In this video, we will discuss the standard normal distribution. If a continuous random variable has a distribution with a graph that is symmetric and bell-shaped, as in the image below, and it can be described by the equation y equals e to the negative 1/2 times x minus mu over sigma squared, divided by sigma times the square root of 2 pi, we say that it has a normal distribution. You won't actually need to know that equation above, it's just part of the definition. We begin with uniform distribution so we can see the following important properties. The area under the graph of a continuous probability distribution is equal to 1, and there is a correspondence between area and probability, so probabilities can be found by identifying the corresponding areas in the graph using the formula for the area of a rectangle. Area equals height times width. A continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. The graph of a uniform distribution results in a rectangular shape. The graph of any continuous probability distribution is called a density curve, and any density curve must satisfy the requirement that the total area under the curve is exactly 1. This requirement that the area must equal 1 simplifies probability problems, so the following statement is really important. Because the total area under any density curve is equal to 1, there is a correspondence between area and probability. During certain time periods at JFK Airport in New York City, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 minutes and 5 minutes. All of the different possible waiting times are equally likely. Waiting times can be any value between 0 minutes and 5 minutes, so it's possible to have a waiting time of 1.234567 minutes. And by assigning the probability of 0.2 to the height of the vertical line in the figure below, the enclosed area is exactly 1. In general, we should make the height of the vertical line in the uniform distribution equal to 1 divided by the range. Given the uniform distribution illustrated on the previous slide, find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. The shaded area in the figure below represents waiting times of at least 2 minutes. Because the total area under the density curve is equal to 1, there is a correspondence between area and probability. We can easily find the desired probability by using areas as follows. The probability of a wait time of at least 2 minutes is equal to the height times the width of the shaded area. So that's 0.2 times 0.3, that should be 0.2 times 3, and that's equal to 0.6. The density curve of a normal distribution is a much more complicated bell shape compared to the uniform distribution, so it is more difficult to find areas. The basic principle is the same. There is a correspondence between area and probability. For a standard normal distribution, the area under the density curve is equal to 1. We use z-score as a score for the horizontal axis, which is common for the standard normal distribution. The standard normal distribution is a normal distribution with the parameters of mu equals 0 and sigma equals 1. The total area under its density curve is equal to 1. It's hard to find areas under a normal distribution manually, but we can find areas for different regions by using technology or by using table A2 on pages 684 to 685. The book recommends using calculators and software over the table, since the software will give more accurate results. But for purposes of the class, the table will be sufficient. If using table A2, it's important to understand the following. Table A2 is designed only for the standard normal distribution, which is a normal distribution with a mean of 0 and a standard deviation of 1. Table A2 is on 2 pages, with the left page for negative z-scores and the right page for positive z-scores. Each value in the body of the table is a cumulative area from the left up to a vertical boundary above a specific z-score. When working with a graph, avoid confusion between z-scores and areas. The z-score is a distance from the mean. The area is a region under the curve. The part of the z-score denoting hundredths is found across the top row of table A2. A bone mineral density test can be helpful in identifying the presence of likelihood of osteoporosis, a disease causing bones to become more fragile and more likely to break. The result of a bone density test is commonly measured as a z-score. The population of z-scores is normally distributed with a mean of 0 and a standard deviation of 1. So these test results meet the requirements of a standard normal distribution. A randomly selected adult undergoes a bone density test. Find the probability that this person has a bone density test score less than 1.27. Note the following are the same. Probability that the bone density test score is less than 1.27 and the shaded area shown in the figure below. We need to find the area in the figure on the previous slide below, z equals 1.27. Using table A2, begin with the z-score of 1.27 by locating 1.2 in the left column. Next, find the value in the adjoining row of probabilities that is directly below 0.07 as shown in the table excerpt below. Table A2 shows that there is an area of 0.8980 corresponding to z equals 1.27. We want the area below 1.27, and table A2 gives the cumulative area from the left. So the desired area is 0.8980. Because of the correspondence between area and probability, we know that the probability of a z-score below 1.27 is 0.8980. Using the same bone density test from the previous example, find the probability that a randomly selected person has a result above -1. A value above -1 is considered to be in the normal range of bone density readings. If we use table A2, we should know that it is designed to apply only to cumulative areas from the left. Referring to the page with negative z-scores, we find the cumulative area from the left up to z equals -1 is 0.1587. Because the total area under the curve is 1, the area above -1 is 1 minus 0.1587 equals 0.8413. The probability of a result above -1 is 0.8413. Even though table A2 is designed only for cumulative areas, we can use it to find cumulative areas from the right by subtracting the area from the left from 1. A bone density test reading between -1 and -2.5 indicates that the subject has osteopenia, which is some bone loss. Find the probability that a randomly selected subject has a reading between -1 and -2.5. We can use table 1A to find that the area to the left of z equals -1 is 0.1587, and the area to the left of z equals -2.5 is 0.0062. The area between these two z-scores is the difference between the two areas found. 0.1587 minus 0.0062 is 0.1525. The probability of a randomly selected subject having a reading between -1 and -2.5 is 0.1525. The area corresponding to the region between two z-scores can be found by finding the difference between the two areas found in table A2. We are frequently asked to find a z-score given a known area or probability. It is very important to avoid confusion between z-scores and areas. Remember, z-scores are distances along the horizontal scale, but areas, or probabilities, are regions under the density curve. Also remember that z-scores positioned in the left half of the curve are always negative. If we already know a probability and want to find the corresponding z-score, we use the following procedure. Draw a bell-shaped curve and identify the region under the curve that corresponds to the given probability. If that region is not a cumulative region from the left, work instead with a known region that is a cumulative region from the left. Use technology or table A2 to find the z-score. With table A2, use the cumulative area from the left. Locate the closest probability in the body of the table and identify the corresponding z-score. In previous examples, the bone density test scores were normally distributed with a mean of 0 and a standard deviation of 1. So they met the requirements of a standard normal distribution. Find the bone density score corresponding to P95, the 95th percentile. That is, find the bone density score that separates the bottom 95% from the top 5%. See the figure below. If using table A2, search for the area of 0.95 in the body of the table and then find the corresponding z-score. In table A2, we find the areas of 0.9495 and 0.9505. But there's an asterisk with a special note indicating that 0.9500 corresponds to a z-score of 1.645. We can now conclude that the z-score in the figure on the previous slide is 1.645. So the 95th percentile is z equals 1.645. For bone density scores, 95% of the scores are less than or equal to 1.645, and 5% of them are greater than or equal to 1.645. For the standard normal distribution, a critical value is a z-score on the borderline separating those z-scores that are significantly low or significantly high. The expression z alpha denotes the z-score with an area of alpha to its right, where alpha is the Greek letter alpha. Find the value of z sub 0.025. That is, let alpha equal 0.025 in the expression z alpha. The notation of z 0.025 is used to represent the z-score with an area of a 0.025 to its right. This means we are looking for a z-score with an area of 1 minus 0.025 equals 0.975 to its left. Using table A2, we find that the value of z equals 1.96 has an area of 0.975 to its left, and thus 0.025 to its right. So z 0.025 equals 1.96.